Excellent. Hi, everybody. All right, so we'll talk about Couchbase Server 4.0, and we'll kind of take the cover off and look a little bit at the inside. So I'll show you the guts of the system. One thing that I'll say is this is a big mention that I'm going to give you a tour of. You're going to see a lot of different components, so it's going to feel like speed dating a little bit, going through a lot of different things all at once. But don't worry, we have sessions that I'll point to that will actually go much deeper onto each one of these components that are very interesting. So this is the talk that will set them up. I'll talk about the entire architecture as a holistic block. And then for each block, I'll actually point you to the session in this section that will go and detail that block quite a bit. I'll start with an introduction. My name is Cihan Biyikoglu. I'm a director of product management at Couchbase. I work on the server product with a whole bunch of people in the team, and I'm a bit of a database geek. I've actually been around for a while. Worked on quite a few databases from Illustra to Informix. How many people know Illustra and use Illustra? OK, all right. Informix? All right. SQL Server? Excellent. SQL Azure? All right. OK, I'm not surprised about that poll. But I worked on all of these products. Couchbase, however, is the best one so far. So, the goals for the session is I really want to get you a quick tour of the mention. I just want to take you into different parts. We'll talk about a variety of different services, and we'll have a chance to dive into it. At the end, though, again, you're going to see a lot of components. So if you missed it, there's a live stream. There's recorded versions of this that you'll be able to come back to and think. There's so much that I got to go through that I'm actually going to ask that you ask the questions at the very end, so that I can see the last slide, and then we can start the questions. Oh, I have one other goal that I should mention. If you're going out on a date, my goal is that some of this stuff will actually impress your date tonight. So let's see if I can do that. All right, so the quick tour is, we'll look at the 10,000 feet view, and then I'll take you through a couple of the components that are super interesting. One of them is connectivity architecture and how we actually manage that. I'll show you what the flow looks like. We'll talk about a replication. It's so central to the product. I think it's important that we actually spend the time to look at some of its properties and how it actually is kind of gluing all of these components together. And then we'll take a look at the cluster manager. It's kind of the governor at the top that really kind of operates the entire infrastructure that we have underneath it. It's fairly complicated. And then we'll dive into each one of these services. The services are kind of a new concept. I'll spend a little more time on them, and especially on the new ones. And then we'll do a quick recap and go. And I have to mention this before I move to my first slide, and I promise I'll get started, is that we're still working on this product. So there are things that will change, and there may be details, minutia, but details that may actually be different in the final version of the product. So just be aware that what I'm showing you is what we have today in the beta that you can download, but there may be changes that we do. So at the very top, kind of 10,000 feet view of the architecture, what we have is the clients sitting at the top. At the top, the clients are smart. The most interesting thing about this picture about the clients is the fact that they actually hold a cluster map. They know where everything is within the cluster. And without a proxy, they can communicate directly with the nodes. The nodes themselves look identical, and that's very much intended. We'd like to keep things simple. But within each node, we've got multiple services that run. At the top, the cluster manager is a piece that is required on every node. It is the governor of the cluster. It will orchestrate a lot of things. The data service, index service, and query service take out a variety of different workloads and independently kind of run these responsibilities. What is really interesting about them is the fact that you can turn some of them off on a given node to create architectures and topologies that are very unique, that you can't really do with other products. So and on every node, we actually have a managed cache and a storage, and every service actually has a fine-tuned set of capabilities that they manage in these core set of services. So in terms of storage, we actually have multiple storage engines based on what we're storing with that service. So the data service stores something different than the indexing service. The needs of the managed cache in the data service versus the index service are different. So we actually have varieties, but these are core services that reside on the entire platform. Now, the interesting thing about turning off some of these services is the fact that you can actually choose also independently the hardware you want to put on these zones that you create. So if you actually take the index service, you turn off the other services, and you create this zone, you can start creating a different hardware that is much better balanced for the type of workload, the index workload that you want to run. If you've got, I don't know, tens or 20s or hundreds of indexes you want to create, you can actually have the hardware designed specifically for the type of indexes that you want to create that may be different, which may have more memory or more CPU than the rest of the nodes that you have. So versus the data service, you may actually choose to scale them out. You may actually get many mini nodes that actually will spread that load over to many different nodes. So it gives you a lot of freedom in the architecture. With that point, let me kind of peel back another layer, and I'll start talking about these individual components and going through this mention that we talk about. So connectivity is the first thing. It's kind of the gate to the mention. This is how there are multiple gates you can come in through. The first one is the admin gate. And some of these gates will actually stay open, or they may actually open and close based on the specific gate that you're at. So REST-based communication is offered through some of these gates, or a stateful online communication is offered through some of these other gates. So this kind of is a laundry list of some of the ones. Imagine the mansion with kind of walls around the cluster, and these are the variety of gates, the most important gates that you can come through. Now, these can all be encrypted. The REST-based communication can actually happen with load balancing across the set of nodes that can offer that service. For example, if you're coming in as an admin, you can go to any one of these nodes and ask the same question, and you will get the same answer. Or if you go to the NoSQL service, for example, it is a subset of the nodes, but you can ask specific questions to NoSQL, and it will understand it. And as I said, there's REST-based communications and online communications that can happen. Now, the workflow for this thing is actually fairly simple. It's about 3 steps. The first thing you do is auth. Before you can walk into the walls of the mention, you have to authorize yourself. The second thing that you do is discovery as a client. The discovery essentially is the process of you understanding the topology of the cluster at that moment in time. It's not a static piece of information. It actually changes over time. So you really need to be able to do that discovery over and over again as the topology changes. But the third step essentially is you came in for a purpose. You're going to do some data access. So let's say you're going to the NoSQL node. You'll go to the NoSQL node, and you're going to work with the NoSQL node. But at that point, there may be changes to the topology. And if that change happens, the client is notified about that change. It will refresh its client, the cluster map, and it will come back in and do the discovery again, and will continue doing the operation. So this is all seamless. These are things that you don't have to worry about. But understand that the client and the cluster manager actually communicate this and coordinate this process together seamlessly in a beautiful ballet. I don't know if that will work for you, but that's the way it works. But essentially, this is the process. So imagine you're on the app node with the smart client. You come in with a key that you want to process. This is more of a key value operation simulation. We'll walk through the steps. The key with the CRC32 will give you a specific node to communicate to, which is the node that happens to be the one that's carrying this key. You can go directly communicate with that node. If another type of key comes in, you can go to another node based on that CRC32 hash. You know exactly where to go. If there are nodes that are added and things actually change, the cluster map is up to date with kind of the smart handling and the retry in the client libraries, and it will refresh the cluster map and we'll know where to go. Now, the second piece that is really interesting about the runtime glue is replication. Replication is very fundamental to the whole product. We use it for, obviously, replicating your data to another node to keep a replica copy in case something fails on a given node. We also use replication, the DCP-based replication, for maintaining incremental map-reduced views. That's the indexing that you can actually use today in 3.0. We have new type of indexes in 4.0, and those actually use replication to maintain themselves as well. The GSI indexes, the global secondary indexes, are actually fed through the DCP replication as well. We have a technology that allows us to push data over to a different cluster on a different geography called XDCR, and that actually depends on replication as well. If you're backing up the system, guess what? It's DCP that's actually feeding you that data. If you're working with Hadoop and you have integrations that you're actually working with, like the Scoop provider or the Kafka connector, all of these things actually feed through DCP. So it's super fundamental to the whole product, and it's important for us to be extremely efficient about that. So there's a couple of properties that make it extremely powerful. Number one, it is ordering. As opposed to some of our earlier protocols, ordering actually helps us resume and keep track of things in very fine-grained detail, which means that we can resume from where we left off under failures. We are actually extremely efficient to be able to kind of pick things back up and continue. It's restartable and resumable. It maintains a whole bunch of checkpoints to allow us to not have to roll back to a very early stage if a failure happens. We actually have much fine-grained resumability with DCP. It's consistent. It gives us a consistent snapshot of the data. So if you're building a brand new replica from scratch, you can actually get a very consistent view and pick up from a given sequence number and just build the rest of the replica with the things that happened since the time you started building that replica. So it is extremely efficient, and it's high performance. So it is memory-based completely. We don't have to wait for anything to get persisted to disk before we can replicate, and that makes it extremely efficient. That is true for all the components that are using it. All right. So those were the two important components and kind of runtime frameworks that really were important to the product. Now what I'll do is I'll actually start talking about the services, the big blocks that were at the top of each node. And cluster service is kind of fundamental. It's almost kind of the patio, the entryway to the cluster. It also orchestrates everything else that happens in the house. So it manages cluster-level operations. You can imagine, who knows what cluster-level operations are? Yes? Give me an example. Excellent. Rebalance, right? Rebalance could be a great operation that needs to be coordinated across a lot of nodes. Placement of data. Oh, that's kind of an interesting problem as to where you put your data based on the V buckets that you're actually going to manage, which are the physical partitions that you actually have to manage. So the membership, right? Nobody can claim, just walk into the mention and claim that they're actually part of this mention. Cluster manager has to register you. It needs to give you the configuration. You have to inherit that configuration as a node and realize that you're part of this cluster. And the cluster manager does a lot of these things. It obviously, things like node status, node health, failover operations, data placement or rebalance, and finally, auth. Cluster manager does the essential authentication at the gates before you can actually come in to the environment for the administrators. So this is kind of a quick buildup of the cluster manager's architecture. I know some of you won't be able to see this at the very back, but maybe you're on the live stream and you can see it. But let me walk through it. At the top, there is essentially auth and admin portal REST API components that sit. These are the listeners that actually will bring in the request and kind of greet you at the door. There's a set of services called the master services. These are essentially required. So within the entire cluster, every node is equal, but there's an elected master that has additional powers. And these are the services that actually reside in that service. So things like the auto failover operations, the actual truth about the topology of the cluster resides in the master, and it is really the full version of the truth. There's a set of services that actually work over buckets. These are things like initiation of your replication between your vBuckets. The bucket essentially contains the vBuckets within the environment. These are the physical partitions. But the bucket itself essentially is a database. There's a set of services that coordinate what they have to do. Things like stats collections and being able to present you a single view of the entire cluster. Those are responsibilities of the bucket service. And per node, we have a set of services that the cluster manager has to provide. Those are things like heartbeats. Are you live? And the node has to say, yes, I am. And that essentially communication, that essential communication is part of the node services architecture. There's a whole bunch of generic services at the bottom, from logging to metadata management that actually reside in the service. But the cluster manager, you can see, is the glue, is the way we actually know about the other nodes, and it's very central. It has an intricate set of things it does during operations, during long-running operations, like rebalance. There are very well-timed operations to make sure that there isn't a realized downtime to the environment. We will actually, this is the operation that you saw when we add a node to the cluster. What happened is, when we brought these two nodes over, we had to tell these nodes to inherit the settings and they have to understand that they're now going to be part of the cluster. Now, it's not only that, we have to move some of the data into these new nodes, and we have to pick which nodes to pick that from, and how to initiate that replication. There could be terabytes of data that are moving around, and that is going to be a long-running operation, and there's a very precise operation that has to happen at the time of completion for us to cut off the cluster communicating to the old replica, but old active replica, and move you over to the new owner of that vBucket, to the replica, which is the new node. So for us to kind of communicate that to the client and the cluster map and make sure that the clients actually now start talking to the new node, and they essentially kind of start utilizing these additional nodes, those are the set of things that need to be coordinated. These are long-running operations, and cluster manager is responsible for doing all of that. So I know I'm not doing this component justice, so there's a talk, if you'd like to listen in a lot more detail as to what this specific component does and what the ballet looks like when it actually does all of these operations. You can go to Dave's talk. This is happening tomorrow at 1 in this very room or area. All right, so let's take a look at the services next. I'll start with the data service. And the data service essentially contains two capabilities. It's the gets and sets. And the view operations are still in the data service itself. So you'll actually kind of, I have an asterisk. I'll talk about the indexing in a little bit in the indexing section. But the core data operations that are the responsibilities of the data service and the data manager are the get set operations. This is the insert, update, delete operations, or key-based lookups. And it's responsible for storing and caching all of this information and providing that. Now, there are two terms, I'm sure. Who knows what a bucket is? Quite a few, but there are people who don't know. OK, I'll explain that. Bucket is the database in our case. And vBucket represents a partition of that bucket, a physical representation of that bucket's partition. It's hash partitioned. We create 1,024 of these things and spread them across the entire cluster. When you, the number do not change, but as you add nodes, each node may actually be responsible for less and less of these vBuckets. So vBuckets are what we distribute across. So just keep that in mind. This is a very kind of a high-level overview of what the data manager looks like. At the top, we've got, I'm sure many of you know, we've got a Memcache inheritance. So the high-speed network I/O capabilities that we have at the top come from the Memcache inheritance. But the listener section essentially manages both the network I/O and the authentication that happens with the service. Now, this is different than the cluster manager authentication. Cluster manager, as I said, is kind of the gatekeeper at the top. But when you start talking to the data service, you still have to authenticate to the service, and you have different privileges here that allows you to get access to data, right? Versus the cluster manager will actually give you much different type of access. The main component here is called EP engine. Essentially, kind of the database engine that sits there, and in each node, it's responsible for managing these kind of vBucket level operations. The vBuckets are essentially on a node can be many. If I have 1024 on a 4-node cluster, you're essentially dealing with about 256, well, exactly 256 vBuckets on that node. Its responsibility is obviously caching the information. It's making sure that you can actually find the key that you're looking for very fast. It manages a set of partitioned hash tables to do this. And you'll kind of see many instances of that depending on the number of vBuckets that are being managed. The checkpoint manager's responsibility is to keep track of what's happening on this node, on this vBucket. It will actually know all the changes that are happening with a set of sequence numbers that are assigned to them. And its responsibility is to keep track of these changes for people who are interested in the changes that are happening to the vBucket, such as replication, right? It's important. Checkpoint Manager does actually something very interesting. It dedupes some of the updates that you may actually see. So it's very efficient in maintaining. If you keep updating the same key, it will actually kind of compress and be able to, within a given window, be able to kind of eliminate some of the updates. So it makes our I/O subpath, kind of the writing of that change, much more effective if you're actually doing a lot of updates to the same key over a given period of time. The item pager is responsible for freeing up the memory. So there are some pages that are not written to disk. There are pages that are written to disk. And item pager will come in and say, well, these pages have been written to disk. I need more memory. I need to free things up. You guys got to go. And it's essentially the responsibility of the item manager. Expiry pager is managing the expiries that happen. I don't know if you guys know, but you can actually set an expiry on each item in Couchbase, and we will honor that. We'll actually have a clock that, and the expiry pager that will come in and do the cleanup, and it's an auto delete essentially, right, for the existence of a given record. The flusher does what it says it does. It actually manages the write operations, and the batch reader does what it says it does. It actually manages the batch reading operations. Now we have a scheduler on the right side of the picture. And the responsibility of the scheduler is essentially to resource all of these operations. So when the expiry pager runs, or the item pager runs, or the flusher has to flush some stuff to disk, it manages a pool of threads, and it will essentially use that pool to resource the requests that are coming in. The scheduler is, to a degree, the way in which it allocates the thread counts for a given node is auto-managed. So based on the number of cores you have, we will actually allocate the correct and smart amount of I/O threads to manage this in terms of readers and writers. You can still manually intervene if you've got a special case, but for the most part, we actually do a good job of auto-managing this piece. Now, this is the operation of updating. It gets into the managed cache, and as a client, you have the option to leave at that point. You get an acknowledgement that it was received by the memory that's on the node that's responsible for that vBucket, and then you can leave. Or you can actually say, but I'd like to wait until this thing replicates to this other replica. Or you can say, I'd like to wait until it replicates and persists to disk on these two nodes. Or you can say, I'd like to wait until it actually persists to disk. So we give you a lot of options on controlling the durability of that write. You can either write to the node, or you can write to multiple nodes and multiple disks on a given call. But DCP-based replication is essentially responsible for managing the replication-based durability, and the disk queue is responsible for essentially persisting the data to disk. So it's a fairly simple picture, but this is the way things work. So hopefully this clarifies it. This is the cache ejection. So as I populate more and more data, we just looked at the item pager. It essentially needs to free up space as more updates arrive. And we may actually eject things out of the cache. That also means that if there's a cache miss, if somebody else actually needs that document and comes back in a second to ask for document 1, we're going to have to go to disk, retrieve that, and pass that back onto the client. And this is kind of the operation that animates that set of steps right here. Now, there's a lot to talk about in this area. There is a session, if you're interested in storage engines, there's a great session from Cihan that you can attend. This is happening at 4:30 in this area. which will unravel and look at some of our new storage capabilities. ForestDB is going to be used only in parts of Couchbase Server 4.0. It's not the main storage engine yet for the KV store for EP Engine, but it is great to be able to see the future, and our indexing actually will use that storage engine in the next version of the product, and we'll eventually progress to use that storage engine more and more. So if you're interested, there's a talk. If you want to go much deeper, Sundar has a talk with Professor Lee Thursday at 2:30 that you can actually go to as well in this area. All right, so the next service I want to focus on is index and indexing. And I think this is where it really gets very interesting. We have multiple options, and I'll actually go through them. So when you look at indexing in 4.0, there are multiple indexers that we actually provide to you. One of those indexers is the view index. This is MapReduce, incremental MapReduce processing that you can actually use. It's the thing that you've been using and you love and all of that. And it continues to be there. You can come through the query API to actually use it. Now, Nickel actually gives you some access to this capability as well. Some limited way, but you can actually create indexes that are indexed by the view indexer in Nickel 2 in certain cases. There's another indexer called Spatial View Indexer. This is the R3 indexer that is going to give you the bounding box type of queries. There's a talk on this this afternoon that you can also see that will detail this. But the interesting addition in this release in 4.0 is the global secondary indexes. This is a brand new type of indexer, and it runs within the index service to give you a whole bunch of interesting benefits, including the ability to independently scale it by pushing it to a subset of nodes and separating it from the data service nodes that are actually running the core KV operations. Now, the reason that becomes interesting is because if you imagine what the incoming KV workload and the indexer has to do, they're always in competition. They're kind of, I've worked on a number of databases, as I said, but there's always this one phrase that you have to put in your documentation as a database. You say, if you over-index, you're actually going to lose some steam on the update performance that you can actually get. So when you actually have a lot of updates, inserts, and mutations that are coming in, you may have to give up the latency effect of that if you have a lot of indexes. Now, the separation allows us to independently scale these two components and limit the impact of these two things competing with each other. The more you insert into the KV store, the more has to be indexed, and that competition can actually become quite intense inside the database. And with global secondary indexes, you can actually prevent that competition. So let's start with the thing you know, which is the views and the view indexer. And I'll describe this. The spatial view indexer is very similar to this in the way it operates. It just happens to build a different type of index for this capability. So there are two components. There's the indexer and then the query processor with the views, with the incremental MapReduce views that we have. There's also CouchStore that is responsible for storing that information. It's separated from the data storage, so you'll see a separate subset of files that are dedicated to the index, and there's a separate path you can set for this thing. It essentially lives within the data service. You should be familiar with the kind of lower right section of that picture. It's the data manager that we just looked at. The indexer sits on the side on the same node and feeds through DCP all the changes that are happening to the bucket that it's running on. So the views will actually feed off of the DCP stream, understand the changes, run the incremental MapReduce operation in a batch so that they can recalculate the index, store that, and they expose a query endpoint, 8092, that you can come in and you can query the index. And the query processor in the view area is also responsible for the scatter-gather operation. So you can go to any node and ask the same question, and it will, for that given index, it will respond the same. There's going to be a node that will govern that scatter-gather, collect the results, and send it back to you. And this is the general architecture of this area. There's a talk on views as well within the operations track. If you want to take a look at this, there isn't a whole lot of changes in this area other than the spatial views, which were experimental in the past, are now completely part of the product in this release. All right, so the new indexer is the one that's interesting that we haven't really talked about. This is the global secondary indexing. And the GSI indexer is responsible for essentially doing the same thing. It needs to maintain an index, and it needs to respond to Nickel for all the scan requests that it actually has. So it's a high-performance indexing capability. The projection router, I'll show you the architecture in a little bit, is the guy who's responsible for keeping track of the changes that are happening on the data service nodes. As you do inserts and updates, we'll actually pick those up, send it over to the index, and projection router runs on the data service nodes and is responsible for communicating back to the index service components what the changes are. It actually does something fairly smart and interesting to make the index building operation very efficient. The supervisor, on the other hand, is responsible for sitting on the node that the indexes are and building the index itself. So it will receive the changes from the projector and the router and will maintain the index. But it also has to respond to Nickel when a query comes in and this index happens to be the one that Nickel picks for your query to be the best one. Underneath the global secondary indexes, we have caching and storage that is magically provided through ForestDB. And that also makes GSI much more effective in the way it indexes and in the way it actually answers questions. OK, so now you know that these services are kind of part of a single node, but they can actually be deployed on completely separate nodes as well if you actually keep turning off services and kind of create these zones. So imagine the arrows to be either local communication or network communication, and based on your topology, we'll actually do that. But in the data service, the operations essentially for indexing starts with the changes happening. The changes come through DCP to the projector and router. The projector and router will actually pick them up, and we'll do something intelligent. It will actually say, well, is this change relevant to the type of indexes that I have on this cluster? And it will understand what is relevant on that update to the set of indexes that exist at that moment, and it will send a packet that's optimized to really only communicate the relevant information for the indexes it's communicating the change to. So essentially what happens to arrive through the DCP stream may be the entire document with the 500 attributes that you actually have in that document, but the projection router may actually be sending much less than that over to the supervisor. So it is to optimize the fact that we can actually communicate a much more effective packet and much less information that's relevant to the supervisor. The supervisor is responsible for picking the changes up from the projector and router, maintaining the indexes. It actually maintains all the local indexes. There's only one of these supervisors that run on a given node that has the index service. And it will pick up the changes that are coming in and maintain the variety of different indexes. And the indexes can be from different buckets, but it will essentially be responsible for kind of looking at these changes and deciding which indexes to send them over to and maintain those indexes locally. ForestDB is the storage engine that sits underneath that powers it all in terms of caching and storage. And finally, the query service, which is Nickel, will actually send a request. So it could be local if you have the horizontal scale-out model where every service is running everywhere within your cluster. But if you've got that isolated, that could be coming over the network. But the Nickel's questions are always going to be about scanning. It's going to say, well, I'm looking for the top customers back in August in 2014. Can you tell me who those are? And it turns out you actually have a nice index that I can use. And that's the question it will ask. And the index scanner will have to respond back with that request. Now, that communication also goes through a supervisor, and that's the interaction it needs to manage. The balance here for the indexer, the intricate balance is to be able to keep fresh indexes and to be able to respond to these high throughput, low latency query requests so that we don't have to compromise on insert update delete latency as well as the query latency as we create more indexes. I'm going to leave it here for the global secondary indexes, but there are two talks I want you to kind of pay attention to. There's one that I will do that will go into a lot more detail about the mechanics of global secondary indexes in the next few hours. And then there's a deep dive that John will do on global secondary indexes that will kind of blow another cover off and will give you a lot more of the guts of the system. And finally, it's the query service. The query service is essentially responsible for running Nickel query execution. It's the query execution engine. It has a number of different parts, parsing and query execution planning. I'm not sure if anybody's surprised about that, but we're very similar in the way in which we actually kind of do that. We receive SQL syntax, We'll look at that. We'll decide what is the best strategy for executing that query, and it will do that. There's an execution engine which will resource that execution plan. It will say, OK, so you want a sequence of operations that are going to filter and their order. I'm actually going to give you the threads, and I'm going to go execute that operation. And it has a pluggable set of data sources at the bottom that allows us to plug in not just Couchbase, but other data sources as well. The pluggability is also interesting from a standpoint of multiple indexers that we want to be able to use. So you'll take a look at this picture and essentially see kind of a visual representation of this. At the top, the listeners are responsible for collecting the query requests that are coming in. The query processor, the parser and optimizer will coordinate, make sure that you've submitted something valid, the SQL that actually is in the right syntax, et cetera. The optimizer will come up with the plan. The query execution engine, as I said, will resource it. On the data sources section, there's a number of things that are special to each data source. So authentication happens to be one of them. The data access, the actual core KV access, is managed by the data portion of the data sources component. The indexer essentially knows about a variety of different indexes, and we can actually expand that box to know about more indexes in the future. But indexer essentially allows us to go to either views or GSI to answer the question. And this is one of the services that will communicate with pretty much everything within the cluster. It's going to ask questions, and sometimes index will actually have the answer. Sometimes it will require the data service to respond to get the full answer back. So again, I'm kind of scratching the surface of this. I'm going to pitch in another talk by Keshav that is going to go much deeper into the specific components in the life cycle of the query and how it maps back to these components. So if you guys want more details on this, I highly recommend this talk today at 2:30. All right. I don't know how many minutes I've got. 4. Excellent. All right. Good. I just want to recap quickly, and I'll open it up for questions. But essentially, there's a couple of things I want you to remember. I know this was a lot. It was, I don't know, sort of speed dating, which component you fell in love with. Hopefully, all of them, but that may be confusing. The essential thing to remember is that we decouple these services. And architecturally, this is very interesting because it allows us to do things that are very unique, where each service can be tuned with its caching and storage. It allows us to control each service a lot more fine-grained. And each service can independently scale. That means that I can take the indexing service, separate it out of the data service, put on a separate set of nodes that may not have the identical hardware. It may actually have more cache so that I can cache more of my indexes. Or it may be a scale-up node with a lot more cores, so I can process a lot more of the lookups independent of the data service partition. And I don't need to add a node, and every time that node has to become an additional partition that takes an equal slice of the work. So it gives us this independence to be able to scale, and that makes it very unique. And with that, I'll open it up for Q&A. Yes, I'll start here.
How do you do in case your microservice does not respond in a timely manner? And the second question is, how do you deal with join overhead in traditional SQL? Because you are back.
Yes. So let me repeat the question. What happens if you actually don't respond in a timely manner? So there are a couple of responses that are interesting in the system. One of them is heartbeat. And if you don't respond to a lot of heartbeats, well, we assume you're dead. There are a set of responses that obviously you can govern through the timeouts that you configure. So you can say, I'm going to run this query, but if it doesn't come back in like 10 seconds or 5 seconds or 1 second, or you may give up. And you get to dictate some of those things. But within the service, there are a variety of ones. Is there a specific one that you're interested in? Or do you want me to kind of walk through?
No, you don't need. I just asked you, how do you deal with it right now and in your 4.0 or in your roadmap? What kind of current status? How do you deal with that?
OK. So in terms of timeouts, we actually give you the control. If you can set very long timeouts for long-running operations and things of that nature. But you get to control the timeouts for the operations that you submit. Within the cluster, we have a lot of timeouts between the services as to how it actually will govern. There's even parts of the indexer that will actually understand the response times of a given indexer node. And if you have identical indexes, we may actually load balance across them based on their response time requirements. But there's a variety of different sections and different things that tackle that.
But timeouts is only one of the couple of problems. Timeouts, they are reason the number of concurrent requests. You might handle like 10 or 100, but they are, I just don't name.
Okay.
Anyway, that's good.
Okay. All right. Maybe we can chat afterwards. I didn't quite catch the detail. The second question I want to answer, though, is how do you deal with the join overhead? So joins are interesting in the way they're configured in Nickel, that it actually allows us to combine documents across in a single query. You can actually take customers and orders, and you don't have to store them together to be able to do this. The lookup, the joins are inherently high performance because we actually force you to do a key-based lookup. And the join itself can actually be an intensive operation if you're joining a lot of records, but we have essentially a streaming capability with the Nickel that allows us to kind of do this operation effectively and generate an execution plan that will do it. There's a talk I'll recommend, which is query tuning for Nickel, where I'll actually talk about joins and how we actually, there are ways in which you can actually tune the join yourself. So I'd highly recommend you come to that, but there are some interesting.
The biggest promise for NoSQL a couple of years ago was no join.
Yeah.
But now, obviously, join was important.
That is true, and I'll repeat that. That's a very good point, and I'll move to the next question. But joins are extremely important, and NoSQL started with no joins. I absolutely understand that. In our case, the joins are somewhere in the middle. We don't need to have you normalizing things to rows and columns, but there's still cases where you want to be able to say, well, products and customers are not things I'd like to put together. But there are certain cases where I actually like to put them together, and it's useful in that scenario. Sorry, yes? Yeah. Excellent. Excellent. So, so the question is, why not? Why not? If I understand this correctly, if I don't really represent your words correctly, let me know. But why not go through a proxy that essentially is a single IP address or virtualize a single IP address that you can actually communicate, and why not do that? The interesting thing is, I think every hop that you add along the way adds to some level of latency, and we are known to be a sub-millisecond latency type database. That's essentially been the differentiation of Couchbase, and we really try to not spend a whole lot of time when it comes to communication. So virtualizing IPs, obviously, yeah, I completely understand, and I've actually done that in the past life, or putting a proxy in the middle that actually kind of funnels everything, adds to the latency, and that's been one of the reasons as to why. It's not to say that we can't do it, it's just that our choice has been to have direct communication with clients and nodes together to be able to make that exchange extremely efficient. Yes? Yeah, so the cluster map is essentially, because you know the hashing algorithm and how the stuff is distributed, you pretty much understand the cluster map is fairly compact in terms of for you to keep, and being able to refresh it, it actually is, there's some capabilities called CPCC that is very cryptic. I won't try to spell it out just now, but we can talk offline, that actually will run ahead of the cluster map or will run ahead of the cluster manager and try to discover what's happening in terms of failures. Because there are network partitioning cases, within the distributed systems that can make things very interesting. So there's an intricate balance of communication between clients and servers on what the topology of this cluster is at any moment in time, and maintaining that both in the cluster map and the cluster manager, and coordinating that across. There's definitely a lot of smarts in that area for us, but we're trying to be extremely efficient and extremely low latency, and that's pretty much the goal for us. Any other? Sorry, I'm being asked to walk off the stage. Thank you very much. I really appreciate everybody coming over. Thanks.